Hello, my name is Frits de Mul and I would like to present some magnetic topics, part B, from my course of Electromagnetism. This presentation is part of a series of presentations about electromagnetism with electrical, magnetical and waves topics and a lot of various other subjects. And these can be downloaded from my website. This presentation has the following contents. 1 to 13 were presented in part A and we deal with 14 to 27. We start with the magnetic dipole, and for the magnetic dipole we use the result for the vector potential, and the vector potential is in the previous slide. Here is the vector potential for a flow tube given by B is the rotation of A, and we derived in the previous presentation an expression for the vector potential written here, with B is the rotation of this expression, mu naught over 4 pi times the volume integral of J over R times dV prime, and this is the definition of the vector potential. The volume integral over the current density in amperes per square meter over the distance to the point P, and for a circuit the integral can be written as 1 over R times dl, and the current density is integrated in the form of the I here. And this result we will use for the magnetic dipole. This is the expression we derived for the vector potential, and we will use it here in point P. But the vector potential is a function of R, and our goal is now to find an expression A as a function of Rp instead of all the R's for the R values over the circuit. Well, this R, 1 over R, can be written as 1 over the square root of the cosine rule here. And R prime is the varying coordinate along the path. Now we take the far field approximation in which R prime, this distance here, is much smaller than Rp and R. And this means that we can approximate 1 over R as given by the cosine rule here. Rp is excluded here from the square root. Is 1 over Rp times 1 plus the first power of R prime plus higher powers here of R prime, and when we do the far field approximation these higher powers can be neglected and we end up with the zero term, and this is called the monopole term, and since this circuit integral is 0, the monopole term is always zeros, and we end up with that dipole term here, R prime cosine phi dl. Cosine phi has to be integrated over this angle here, over the circle. And this result we will use in deriving the dipole moment for the magnetic dipole. Here is the situation for a circular circuit, and the radius of the circular circuit R is much smaller than Rp. Assume that P is in the YZ plane. That means no loss of generality. And when we calculate R prime cosine phi, we can do that using the scalar product of the two vectors, ER and R prime. Suppose it is under angle alpha. Then ER is 0 sine theta cosine theta, because P is in the XZ plane, and this is the ER prime is R sine theta minus R sine theta plus R cosine theta 0. And when we calculate that, you end up with R sine theta cosine alpha. Only the component in the y direction will contribute. Now, dl in the expression here is along the circuit. So it can be written as RdA times minus cosine alpha. That's the dl component here. It's RdA times minus cosine alpha. And so AX can be written as mu naught I over 4 pi rp squared times the integral over r prime cosine phi is r prime cosine theta times RdA, and RdA is the line element, RdA, dl, times minus cosine alpha. Minus cosine alpha. And thus it can be written as the integral of r squared sine theta over times the integral of minus cosine squared alpha, and then you end up with mu naught I over 4 pi r p squared times r squared, the radius of the circuit, times sine theta over p. And this means also that the AY and AZ will be 0. There's only an AX component. In point P. Here we have ERP, here we have EN, and when we define the dipole moment as M, factor M is the current times the area times En, or I pi r squared En, then we end up with A, the vector potential, is mu naught over 4 pi rp squared times the factorial product of M times ER. Now we switch in topic 15 to magnetization and polarization. And suppose the magnet is a set of elementary circuits, and we have n circuits per cubic meters. The total surface current will be I total, and the total magnetic moment will be I total times the surface times En, and En is the normal vector on the cross section. Now the definition of the magnetization is the magnetic moment per volume, and as you can see here, the magnetic moment, and that is the surface current divided by the length, as it is seen here, surface current divided by the length. When we compare polarization and magnetization, we have, in the polarization case, the dipole moment in Coulomb times meters, charge times distance of the charges, and here the dipole moment in amperes times square meters, the surface. The polarization is given by P is n times P, in which n is the number of charge particles per cubic meters. And so the polarization is Coulomb per square meter, or the surface charge per square meter. And the magnetization M is the number of elementary circuits per cubic meters, so the number of coils per cubic meters, and that is given by ampere per meter, and can also be written as the surface current per meter. Topic 16, the magnetic circuit. We have it here. This is the blue circuit, and in black arrows is the magnetic field. This is the top view. We have forces F here introducing a torque on the circuit, force F, and B is the length of B is the width of the circuit, and L is the length. B is the width, so this distance here is B sine theta. The torque moment will be tau is force times distance, B sine theta, is I BL times B sine theta, I times B times L, that's the force, is IBS sine theta. S is the surface of the area of the circuit. And the magnetic dipole moment M is IS times the normal on the circuit, and thus this means that the torque moment tau is the vectorial product of the dipole moment, magnetic dipole moment, times the magnetic induction. And this also means that the tau is directed perpendicular to the F and the B and the M. So directed upwards, out of the plane of drawing. The potential energy for the magnetic circuit is given by minimum for theta is 0, because then the field, the circuit is directed with its magnetic moment along the B field, and the maximum is for theta is pi, and thus we end up with the potential energy is m times b times cosine theta. And m is the magnetization here, and this means that it is equal to the minus the scalar product of m and b. And compare for the electrical dipole is minus the dipole moment times the external field, and for the torque we found is the dipole moment with the factorial product with the external field. Now we will compare an electrode and a magnet. Electrode and magnet. In the electrode, the electric field is given by d minus p over epsilon naught, or in another way, the displacement is epsilon naught times E plus P, and P is the polarization here. In the magnet we have a similar situation. We have the field strength is the induction over mu naught minus M. So we can write B is mu naught over times H plus M. Here we have two interface crossing relations. This is the circuit straddling to the interface, and here we have the Gauss box. And for the Gauss box it holds that in an electrode the free charges are 0. Here we have the interface crossing relations for the H and the B. Here the H is this is the Ampere's law for the H, and this is the B. The polarization is from minus to plus, and the magnetization, suppose all the magnetic moments of the volume elements are directed along each other in the upward direction. For the E field we found that the integral over the circuit must be 0, so outside it is from above to below, and inside it has to be the same. For the H, the same. The rotation, the circuit integral will be 0. The rotation is 0. And for the D, the integral should be 0. And for the B, the same. And now we go to the B and H field at an interface. Given two materials, 1 and 2, and in material 1 the induction is given as BE, B1, and also the permeabilities are given mu1 and mu2. And the question is calculate B in material 2. We need the two interface crossing relations. Here we have the Ampere's law, and here the Gauss law. And we have the material relation between H and B. B is mu naught mu r times H. The two interface crossing relations are the Gauss box and the Ampere circuit. First the Gauss box. there is no charge or something like that inside, and so it means that B times A cosine alpha 1 is the normal component, and here is the same for the second surface. That will be 0, so the normal components, perpendicular components of the magnetic induction B is maintained, will remain the same. For the circuit, there is no current inside, and this means that the parallel components of the H will be the same. When we divide these two relations here, then we end up with the ratio of B and H for material 1 divided by the tangens will be the same for material 2. And when we cancel the A over L, we end up with mu R1 over mu R2. The ratio of the mu's is the ratio over the tangens. And compare for dielectric materials, we found that the ratio of the epsilons is the same as the ratio over the tangens. Topic 19 is about a toroid with an air gap. Here is the toroid. There is a solenoid. The toroid has a radius r. It is a thin toroid. The radius here is exaggerated enormously. The core line has radius r, and we have a length L, number of coils n, and we have a mu r. In the air gap, the mu r is 1, and the width of the air gap is much smaller than the radius r. And we will use the indices G for the gap and M for the metal. The question is, determine the field strength in the gap. We have the following relations, interface crossing relations. The current integral over the H is the free current, and the Gauss box over the magnetic induction, and that will deliver 0. And we have the material relation B is mu naught mu R times H. Here we have the Gauss box. The distance between these two metal surfaces is d. And the ampere law will deliver us hg times d plus the integral over the path. That is hm in the metal times L minus d is N times I. That's the current that is enclosed. The Gauss box delivers us with Bg is Bm, normal on the surface. So Bg is given also by mu naught times Hg, and Bm is given by mu naught mu R times Hm. Now we have enough to calculate the result. Hg is mu R times the total current, N times I, over L plus D times mu R minus 1, and Hm is given here. And this means that in the gap the Hg is proportional to mu R times the number of coils. So this means that the field in the gap is growing when you increase mu R and you increase the number of coils. Now we go to induction. Induction. Suppose we have a conductor of an arbitrary shape and it's moving in a field B. Here is the field B. At time t, the current is in position L1, and at time t plus dt is in position L2. And the question is, let's show that the induction potential along the wire, or the path integral here, can be written as the time derivative of the flux through that circuit. To do that, we use an artificial Gauss box, and we use for the top lid the surface S1 in position L1, and for the bottom lid S2 in position L2. And then we can write Gauss, and since Gauss must be 0, then the integral over the wall must be the same as minus the integral over the top and the bottom. So what goes in the wall has to go out through the top or the bottom. And this is given by minus V at t plus V at t plus dt. This is the top, this is the bottom, and this is dVt. So what's going in the wall is going out through the surfaces. Now let's take a surface element here with an area V dt, because this is the distance between S1 and S2, and a line element along the circuit dl. And the area here is V dt dl times the cosine of theta. This is the area. And so we can write for the integral over the wall is b times en op the wall times ds, and ds is v times dt dl sine theta. E times en is the normal vector on that wall element times that wall element itself. Is the path integral of b times v dt times dl, the b times v dt times el, so we have times dl here. This is the expression for the sine. This is the same as what's here in these points, except for that we have taken the direction of en inside the dl. And this can be written as dt times minus v times b times dl, just for a rearrangement of the factorial product. dt times the path integral of minus v times b times dl. And thus you can see that when you divide this d phi t, as seen here, d phi t, divide by dt, then you end up with minus v times b factorial product, and that factorial product has a scalar product with dl, and since v times b is the electric field strength of the Lorentz force times dl. And this means that with that En, that's a non-electrostatic field, there are no charges, no separate charges involved. And so we have showed the equivalence of a potential difference here integrated over the path is minus the change in the flux, minus the time derivative of the flux integrated over that area here. Now let's go on to Faraday's law. Static, we have here that the circuit integral over the E is 0, because there is no movement. Dynamic, suppose the flux changes in time or through movement, then the situation is different. We will have a non-electrostatic field En. And this means that we have a V induction is the path integral of En dl is minus d phi dt is minus the changes in the enclosed flux, as we have seen just a moment before. Now, let's see the consequences. Suppose we let circuit C shrink and we keep S constant. This means that we have some kind of situation here. This is surface C, this kind of volume, and this is the circuit C that's shrinking. We can shrink surface C to a point, and then it virtually disappears, and then we have a closed surface here, closed surface, BDS is 0, and this means that this path integral of E and dl will be 0. For a closed surface we will have that E and dl is 0. Because suppose the B is changing, the same flux will go in and out at any time. What is the induction in a rotating circuit frame? Here is the frame in blue with B for the width and L for the length. This is the external field, and here we have theta. And suppose the frame is rotating with rotation velocity omega in radians per second. Well, omega here has a connection with the angle theta. Theta is omega t, and we have assumed that at t is 0, theta is 0. The velocity is omega times half b. Now, what is the induction potential difference? We can do it using the Lorentz force, and with the Lorentz force we have here the ENs, the electrical field strength of the Lorentz force, and we can derive that from V times B, and then we end up with those green arrows here, V times B, and then we have the path integral of V times B times dl is 2 times L times V times B external sine theta, 2, and that is the consequence of the factorial product, the sine of the theta, is 2 LV B external times the sine of omega t. And when we use the flux change, V is minus the phi d tau, is minus d dt of the surface integral of the external field, is minus the external field times LB cosine theta, because this is the changing surface along the field, using the cosine of the angle between the circuit and the field. And so this ends up with B external times LB omega sine omega t, and that's the same expression as we have seen here. Topic 23, electromagnetic brakes. The question is, why is a conducting wire decelerated by a magnetic field? This is the situation. We have two rails with a switch, but the switch is open, and we have a cylindrical rod here, and there is an external field, and the rod is given a velocity v in the direction of the rails. Then the electrons feel a force in the perpendicular direction here, and that Lorentz force is causing a potential difference between the ends of the rods. One end will be negative and the other end will be positive. This is the Hall effect, and this means that there will be an electrical force that is growing until it is equal to F Lorentz, and then we have a balance, but no braking, because no force in the direction of or plus or minus v. Now we close the switch, and then the force will move the electrons, but the electrons will assume a velocity in this direction, and this means that there will be a current in the circuit, and that current in the circuit will be in this direction here, from P to Q. And this causes current, and this current will cause a second Lorentz force, and the second Lorentz force will be counteracting the velocity. And the second Lorentz force will cause an electrical field with negative charge here and positive charge here. And this works on the ions, the positive metal ions, and they will feel a force, F ions, and that force will act as a braking force. Coupled circuits. Suppose we have circuit 1 with current I1, then part of the flux from 1 will pass through 2, and that is phi 2 by 1. And phi 2 by 1 is proportional to the current 1. And now, by definition, the proportionality constant is called the coefficient of mutual inductance, or mutual inductance. And it's given in terms of Henry's, and here we have the dimensions of the Henry. It's derived from the flux divided by the amperes, and this is the coefficient of mutual inductance. And these definitions are from the definition for the field times the area. And suppose circuit 2 has a current as well, current I2. Then the flux through 2, V2, is composed by the flux caused by 1 and the flux caused by 2 itself. And here we have the mutual inductances, M2 by 1 and M2 by 2. M2 by 2 is called L2, definition, coefficient of self-induction, or the self-inductance, L. And M and L are geometrical functions. The functions on the shape, the orientation, the distance of the circuit, and so on. We can use that result in topic 24, the toroids, in which we have N coils with current I1, and here we have N2 coils with no current at the moment. This is cross-section S, and we have a core line, average line here, and the flux from 1 through S will be, phi S is B times S is mu naught mu R N1 I1 S over L. Now, the linked flux from 1 through 2 is N2 times that flux phi S, as is given here, N1 and 2. Now we can calculate the coefficient of mutual induction in 2 by 1, originated by 1, is mu naught mu R N1 1 and 2 times S over L. And as you can see, this expression is symmetrical in 1 and 2. So the mutual induction is symmetrical. And this result is generally valid. Mij is Mjy. The self-inductance of a coax cable. Suppose we have radii A and B, A and B, length L, and current I. And the choice if the current is inside is the upward direction. For the tangential field, it holds that Br is mu naught mu R I over 2 pi R. And of course the tangential field is only present in between the two surfaces, not outside or inside the tube here, if it is a tube. The flux through the circuit, and this circuit here, Gauss circuit, is given by the surface integral over the B is the surface integral over dl, and dl is along the length, dl, times the integral over dr, and dr is along the radius, and along the radius the induction varies, the B, and it varies with 1 over r. And thus we end up, when performing the integration, by mu naught mu r I times L over 2 pi times a logarithmic term, the logarithm of b over a, the two radii. And this means that the self-inductance per unit of length is given by this expression here. And you can achieve a large self-induction by having a small value of a, or a large value of the ratio, of course. Let's compare with the capacity of a coax cable. That's given by C is 2 pi epsilon naught epsilon r divided by that logarithm term. Now we discuss the magnetic field energy. Suppose we have a circuit C in the xy plane. Then there will be magnetic field lines around, circles around the circuit here, circles around the circuit. And perpendicular to those circles, we can construct surfaces called A surfaces, and they are everywhere perpendicular to the H or B field lines. Now, the flux through those A surfaces is B times dA integrated over the closed surface A. And the magnetic energy is 1/2 times L times I squared. And what is that volume element of the surface element here? That's the surface element here. This is the green lines are the two equipotential surfaces, and the red lines are the H lines here. This way. This is perpendicular to each other. And this means that it is the L is half the same as B, half times B times H integrated over the surface, and the length is, and the surface here, that's here, we have here the cross section over that surface element dA, is 1/2 times the surface integral over dA times the circuit element over dL times B times H, and that is given by 1/2 times the volume integral over B times H. Compare the electrical energy. A of electrical energy is 1/2 times the volume integral of D times E, the displacements, times the electric field strength. Finally, let's talk about Maxwell's fix of Ampere's law. This is the induction Gauss law, in which a non-electrostatic field, and circuit integral is minus the time derivative of the magnetic flux. A changing B field causes an electric field. And the question is now, Maxwell said, does a changing E field cause a B field as well? Suppose we charge a capacitor using a charge current density J. Then the circuit L encloses a surface S1, and then the relation holds that the surface integral of the path integral of BdL must be the surface integral over the enclosed surface of the current density. This is Ampere's law. Now we change the surface a little bit, and from S1 to S2, and L encloses S2 as well, and this means that also for the surface S2 the same Ampere law is valid. Now we enclose now we look at the volume enclosed by S2 and S3. And with S2 and S3, on one side we have the current here, and on the other side we have some kind of flux change. The current change here is the change in the displacement. So the current in fact is the change of charges. This is the change of charges on the plates, and the change of charges can be written in the form of a change of electrical displacement integrated over the surface. And when you assume that L, that circuit here, the blue circuit here, L, encloses S3 as well, then you also can write the path integral of BDL is mu naught times the time derivative of DDS. And in general we have the path integral of BDL has a term taking care of all the current flowing through S, and a term taking care of the changes in the electric displacement of charges present in the present in the field. And this is the fix Maxwell had for Ampere's law, and it will be used in the electromagnetic waves. And this is the end of presentation.